So this is higher unit 2. This video is going to be on fats and oils. Okay, so first of all, what we need to know is that our diet is made up of our daily plate. Okay, so that daily plate includes carbohydrates, proteins, and fats and oils, all of which our body require in order to function on a normal basis. Okay, so what you need to know the definition for the purpose of fats and oils is that fats and oils are a concentrated source of energy, and they're essential for the transport and storage of fat-soluble vitamins within the body. So that's something you need to remember. Fats and oils are a concentrated source of energy and are essential for the transport and storage of fat-soluble vitamins within the body. Okay, so it's important that you know that fats and oils are a dense source of energy. So what that means is there's a lot of energy in a small portion. So for example, there your avocado. Avocados are quite small, but you get a lot of energy in them, okay? That's in comparison to carbohydrates and proteins. Fats and oils, you get more energy in the same mass. Okay, so why are fats and oils so important in our daily plate or in our bodies? So the fats and oils are non-polar molecules. So we know that polar dissolves polar, non-polar dissolves non-polar. So what happens is the fats and oils are required in our bodies so that non-polar vitamins can dissolve in them, okay, because they're not going to dissolve in water. So they dissolve in the fats and oils, and that allows the vitamins to be transported around the body, okay, only because like dissolves like, and fats and oils are non-polar. Okay, so looking at the structure of our fats and oils, in every single fat and oil, the backbone structure is your glycerol, okay, and the systematic name for glycerol is propane 1,2,3-diol. So it's really, what you need to know is that basically fats and oils are like multiple, so there's 3 here, ester bonds. So you're going to join onto a fatty acid here, and you're going to join on using a condensation reaction. Condensation, the byproduct is water. Okay? These join in a 3-to-1 ratio, 1 glycerol molecule to 3 fatty acids. So what happens is the fatty acids adds on here. Okay, so you've got 3 all joined to 1 glycerol molecule. Why can that happen? It's because of the 3 hydroxyl groups, the triol part of it. Okay, so here we've got the structure of a fat. Okay, so we can see our glycerol molecule here. Okay, so that's the backbone of my fat molecule. And here you can see we've got long chains, long non-polar chains. Okay, so this is where these non-polar vitamins basically dissolve. They're going to be soluble, so they're going to dissolve in there, and that allows them to be transported around the body. Okay, so fats are saturated molecules. Remember, saturated means single bonds. So my fats contain carbon to carbon single bonds. And that's what makes it a fat. So we've got 3 fatty acids. That's what these are here. Look, you get to start your carbonyl group there. So 3 fatty acids, all bonded to 1 glycerol molecule. So fats are saturated. What's the difference between fats and oils? Oils are unsaturated. Okay, so they react with unsaturated fatty acids. And remember, unsaturated means carbon to carbon double bond. So what happens to the structure when it bonds to an unsaturated fatty acid? Because of the carbon to carbon double bond, the chain, so the straight chain, is distorted. Okay, so it goes out of shape. It's not a long straight chain anymore because of this carbon to carbon double bond here. And that's the only difference between fats and oils. Fats are saturated, oils are unsaturated. Okay, So they look like this in a diagram. We draw them like this because it's easier to draw due to the large complicated molecules, the large complicated fatty acid. So you've got one joining on here, one joining on here, and one joining on here. That's equivalent to your glycerol looking like this. So you've got your hydroxyl group at that side, one at that side, and one here at this side. Okay, so that's equivalent to that. What we like to look at molecules, we like to see them straight chain. Okay, so fat molecules are straight chain. They're going to look something like this. It takes the shape of a kind of tuning fork, and you've got two fatty acid molecules on one side, one on the other. Your oils take the same structure, but because of these carbon-to-carbon double bonds, because they're unsaturated, it means that we've not got straight lines. Our molecules aren't in straight lines. They are bent round a bit, they're distorted, and it's because of these carbon-to-carbon double bonds. Okay, so this causes something else to happen as well. So think of your van der Waals forces here. Okay, so fats tend to have a higher melting boiling point than oils, and this is because of the stronger intermolecular forces. So fats have stronger van der Waals. Why do fats have stronger van der Waals? So they have stronger van der Waals because the molecules can pack very, very tightly together. Because they are straight chain. Okay, so when they pack very, very tightly together, they're going to have stronger van der Waals, and we know that in order to overcome them, to melt it, you're going to have to put in more energy. So fats are solid, saturated, and contain single bonds, carbon-to-carbon single bonds. So the triple S, solid, saturated, single bonds. Whereas when you move on to oils, because your chain's been distorted, they can't tightly pack. They can't pack as closely as what a fat would do. Okay? So that means that their intermolecular bonds aren't as strong as they were in the fats. So it doesn't take as much energy to overcome, which means these oils are liquids at room temperature. Okay? So the more carbon-to-carbon double bond there are, the lower the melting point. Okay, so more carbon-to-carbon double bonds, the lower the melting point, because the more double bonds there are, the less it can get tightly packed together because the double bonds distort that chain. So oils are a liquid at room temperature because of this. Okay, so how do I get an oil to form into a fat? How could I change the molecule of the oil with the carbon-to-carbon double bond to get them into something like a fat molecule where it's nice, straight chain, everything's very rigid. So I can do this by what we call as hardening of oils. Okay, so what we do is we add on hydrogen. So remember, a carbon-to-carbon double bond, you add on hydrogen, you break the double bond. So what we do is we add on hydrogen with a nickel catalyst, and this is called hydrogenation. Okay, so hydrogenation is the adding on of hydrogen. So here you can see this, you've got 3 double bonds. We're adding on 2 molecules of hydrogen with a nickel catalyst, and these have broken 2 of the double bonds, leaving 1. If I was to add on another molecule of hydrogen with my nickel catalyst, I would then break this carbon-to-carbon double bond also. So margarine is an example of hardened vegetable oil. Okay, margarine is very similar to butter, and you use it to obviously put on your toast or on your pieces or something like that. Okay, so what's happened to the margarine? Margarine started as an oil. It's went through hydrogenation, so hydrogen and a nickel catalyst, and here we have a fat. So margarine is classed as a fat, okay, because it's been hardened in order to become more of a solid. So fats versus oils then. Okay, so the only difference between a fat and oil is how unsaturated it is. Fats are saturated molecules, so they only contain single bonds, whereas oils are unsaturated molecules. They contain carbon-to-carbon double bonds. How can you test how unsaturated your oil is? Well, we know the test for unsaturation is bromine water decolorizing quickly. So the more carbon-to-carbon double bonds the oil has, so the more unsaturated it is, the more bromine is going to be decolorized. Okay, so here if you're thinking about this, the more unsaturated my oil is, in here, the more bromine you're going to have to put in order to decolorize. Okay, so looking at this, if we know fats and oils are made through condensation reactions, how do we break that back down? We break that back down by adding in water through a hydrolysis reaction. Okay, in the hydrolysis of a fat, you get a 1:3 ratio, so you're going to get 1 molecule of glycerol and you're going to get 3 fatty acids back. Why am I getting 3 fatty acids? Because I have reacted 3 fatty acids in the first place to get my fat or my oil. Okay, so it's a 1:3